We now welcome Mattia Manucci. He's working in the Gran Sasso Science Institute, and right now he's going to give us a talk regarding contour integrals and also reduced basis models, so before, for dynamical problems. So thank you, Mattia.
Thank you. First of all, I would like to thank the organizer for giving me the opportunity to speak in this nice location. This is, I will speak about my PhD topic, and it is the decoupling of these two methods, contour integral method that I use to solve ordinary differential equation, and then reduced basis, which fortunately you had the talk of Gran before that spoke about model reduction, and this is always the same framework, so it will be much easier for me to explain now. So this is the outline of the talk. At the beginning, I will just introduce the contour integral method, and I will explain what they are. Then I will move to the reduced basis method, and as before, I will give a brief introduction to the topic. And then I will treat reduced basis method for time-dependent problems, and then I will move to the coupling of the two tools, and then I will show some numerical example, and I will move to the conclusion. So let's see what the contour integral methods are. So we look to this type of problem, so time-dependent partial differential equation, where the operator here, A, can be any linear second-order differential operator. So you can think to this as a parabolic equation. The only things that we have here is that both the linear operator and the source term, they also may depend from parameters, okay? So scalar, typically. So we assume to have a suitable discretization in space, and therefore we have to deal with an algebraic equation, okay, vector and matrices. But still we have here the dependence from the parameters taken into account. And then what we do is that we want to apply the Laplace transform to this algebraic equation, and so we have that. To get the Laplace transform of the solution on a point z of the complex plane, we need to solve this linear system. Okay, here I wrote the matrix, the inverse of the matrix, but just bring it to the other side, and then it's a linear system that you have to solve. Okay, and then we want the solution on the time domain, so to go back we apply the anti-transform. And this is given by the integral over a curve gamma of infinite length, which keeps all the singularities of the integrand function on its left, and go to plus and minus infinity on the imaginary axis. Okay. And this is what we have to integrate. So what the contour integral method they do is to try to place and to approximate this curve. Okay, because in principle we cannot integrate over that, so we need to parameterize the curve and then to approximate the integral with some quadrature rules. So what we did, okay, there are two works in which we refer, and we use this integration contour, which is an half ellipse joined with two half lines, and here is how it's parameterized. Okay, so let's say all the methods is how to place correctly this integration contour. Okay, once we have defined the map for the integration, okay, we need to truncate the integral because we cannot integrate over an infinite length. And okay, so we will truncate it, and then we will apply a quadrature rule, for instance, a trapezoidal quadrature rule. Okay, so this will be our approximation. Okay, this is the integrand function evaluated on the quadrature points. But the nice features that we have here is that, okay, if we want to measure the error between the original solution and the one we approximate by the integrals, we have three components of the error. So, as always, there is a component due to the noise. Indeed, here, at every quadrature point, you see, we have to solve a linear system. So, when we solve a linear system, then if we have noise on the initial data, then it will be propagated depending on the conditioning of the system. And then, okay, we have the truncation of the integral, so we are neglecting some part. And finally, okay, we have the quadrature error that we introduced using the formula. But the next feature is that we have, even if it's a simple trapezoidal quadrature rule, for the properties that we have in the framework of complex analysis, here we have an exponential convergence with respect to the number of nodes. So that's nice because, I mean, if these two components we can control, placing in a good way the integration contour, finding a good parameter C where to truncate it according to the tolerance that we want. Okay, once we fix these two components, then here we will need normally a small number of nodes to reach the target accuracy we want. The only thing is that this constant p can be very large, but fortunately we can also control this because it depends on how we place the integration contour. So important feature is that also the number of nodes can be halved because we are integrating a symmetric function on a symmetric profile, so we can also halve the number of nodes. Okay, so there is an important set we have to look to place the integration contour, and this is the epsilon pseudospectrum, which is defined in this way. So it's the set, the epsilon pseudospectrum of the matrix A is the set of all the points in the complex plane for which the norm of the resolvent, this is called the resolvent, okay, is less or equal 1 over epsilon. Okay, actually what we look is the weighted form of the pseudospectrum, and because we multiply it by the real part of the point in the complex plane times the time where we want to evaluate the solution. Okay, this set is very important. The idea is, I mean, can be understood very easily because, okay, we have to solve linear system of this kind. Okay, so if we control the norm of this matrix, it means that we also control the condition of the matrix. And if we control the condition of the matrix, then we know about the noise that we are injecting in the system, and we can also control the constant p on the part of the error due to the quadrature error. So just as a recall, this norm to the -1 is equal to the smallest singular value of the matrix Zi minus A. Okay, this is just an example on which different result one can have if place the integration contour in different ways. So this critical curve is built according some target pseudospectrum level curve. So let's say if in this case, the first case here, we are very close, and indeed we want to reach an accuracy of this, we require an accuracy of this kind, but we don't manage. And also to reach the plateau we need a large number of nodes. In the second example, okay, we are far, but probably too far from the critical set. And so we need, we reach a target accuracy, but we need a lot of nodes to do this. Okay, this is another example where due to we have large condition number because we are very close to this curve. So here the component due to the noise is very high, and indeed we don't reach the accuracy. And finally, this applying the method, we find this integration contour, and indeed here with 15 nodes we reach a very high accuracy. Okay, so just to mention that, okay, I said that we go back with the Laplace transform, with the inverse Laplace transform, and we compute the solution at time t. So only at a specific time we can do this. The truth is that actually, let's say, all the dependence in time is only in the exponential term, which is a scalar. So all the effort in the numerical procedure is in the computation of these linear systems. And so indeed, the idea is that, okay, if we place the integration contour in a smart way, then we can compute the solution on the continuous time window, computing only the Laplace transform of the solution on the quadrature points. We compute this only once, and then for all the time window, the continuous time window, we can compute the solution on any time instant. Okay, this was, let's say, the introduction on contour integral methods. Now I move to reduced spaces. So okay, before Gerald did model reduction, here the context is always, let's say, we want to solve a linear system of smaller size. It's always the same. But the fact is that we want this because we have parametric problems. So maybe here we don't know, once we want to simulate a large linear system for many values of the parameters, okay? So if the system then is very large, all this computation became very prohibitive. So the idea is that, okay, we want to try to reduce the size, controlling the error also, and then to run for the new instance of the parameter to solve the reduced problem. So what is done typically is we define this map that goes, you take an instance of the parameter and the associated solution of the problem for that instance. And then this set, which is basically the set that contains the solution of the problem for each instance of the parameter. Okay? And then it's defined this quantity, which is called Kolmogorov and width. And okay, what this measure? Basically, this measure how much this set, so that is called the solution manifold, can be well approximated by a space of dimension n. Okay, so clearly, this as we enlarge n, this quantity has to decrease because we are taking bigger subspaces or spaces, and with bigger spaces we approximate better and better the solution manifold. Okay, so the assumption is if this quantity is has a fast decay, say exponential, for example, then okay, the idea is that with a subspace of a small dimension, we can approximate all the set of the solution. Okay, so this is the full problem. Right? Here I have no time. Just say you can see just a linear system of size and age, which can be very large. And so the idea is that okay, assume that we have this reduced space of size n r with dimension much smaller than n age. The idea is that we can approximate the reduced solution as a linear combination of the base vector of the reduced space, okay, which are nr. And then, okay, so this will be the form of the reduced solution. And if we want to compute it, we need to compute the coefficients. And to do this, what we do is that we plug this reduced solution on the system, okay? And now, of course, the equation will not be anymore exact, but we will have a residual. And we ask that this residual is orthogonal to the reduced space. This is what is called the Galerkin projection. Okay, so this is the set. So this is how we write the solution, and then we ask this condition. So the residual has to be orthogonal, which leads to these constraints. Okay. Okay, under the assumption that the problem is coercive continuous, so under this hypothesis, what can be seen is that the error between the solution of the full problem and the solution of the reduced problem, when we evaluate it on subspace of dimension nr, let's say decays with the same order of this Kolmogorov and width. So if this has an exponential decay with respect to n, also this error will decay very fast, and therefore we will just need a smaller subspace for the approximation. So here, okay, this technical assumption is that all this works if we assume that we have this fine decomposition of the operator. So basically, that we can write the matrix as a sum of matrix that do not depend from parameters and scalar functions that multiplies this matrix and that depends from parameters. Otherwise, if this does not hold, one has to apply interpolation techniques like the DYNAMICAL or other things. Okay, so if this hold, and for our problem it's all linear, so it's always hold. Then what we can do? Okay, we have this matrix containing the base functions of the reduced space, so it's of size nh times nr. Okay, and what we do is that we can pre-compute on an offline phase the reduced operator and also the known term by multiplying from the left and from the right with for this matrix. And at the end, what we'll have to do is to reduce to solve this problem of size nr. Okay, just an example. This is a diffusion convection reaction equation, and so okay, we have we discretize it. Okay, so we have discretization of the second derivative, first derivative, and the identity basically. And so okay, we have this discrete equation, and so here which are the parameters are the diffusion coefficient, the velocity, and the reaction term. So this is the vector of the parameter, and these are the metrics that do not depend from the parameters, and how we write them the whole matrix, right? Okay, and these are the three parameters, and the same for the source term, and then this is the system. Okay, for now I said I assume that we have the reduced space, but this space has to be constructed, and what is done in reduced space is that a kind of greedy strategy is used. So this is an iterative procedure where at each iteration a new basis function is added in such a way that then the overall precision is increased. To do this, we need an error estimate, so we need an upper bound of the error to do this. And then we proceed with the following scheme. So we find the parameter which maximizes this error estimate. We compute the solution, also called a snapshot, for the distance of the parameter, and we add it to the reduced space. And we iterate this procedure 1 and 2 until the error estimate is smaller than a prescribed accuracy for each instance of the parameters. So the important feature is that this error estimate has to be cheap to evaluate, because in principle we could say, okay, our error estimate is the error, no? But the error means that we have to compute the solution of the full problem for each instance of the parameter, and this is something we want to avoid. So really here we only ask that it has to be cheap to evaluate, and of course it has to be an upper bound. But this strategy has to be proven theoretically that it works. Okay. So what we do for a time-dependent problem? Well, always we rely on error estimate. So we find when we use time-stepping methods to discretize in time, we find then the parameter which maximizes the error estimate. We compute the solution at each instance of the parameter. Okay, so we will have a set of solutions, and then we have to compress the information here because there can be a lot of time steps, and to inject all of this in the reduced space, well, then we lose the small dimension of the space. So we compress the information by doing a singular value decomposition. And then, okay, we compress and we add what we want to add to the reduced space. And we iterate the 3-step, okay, as before. The other approach is space-time variational based method. So here, time is considered as another spatial variable. So it's all discretized, the size of the problem will be larger. And this is what is done in literature for the moment. So now the idea is of my work is this. So we approximate of the problem as with a quadrature rule. So it's a linear combination of the integrand function evaluated on the quadrature points. So what we can do is, we can build a reduced space using as snapshots the Laplace transform evaluated on the quadrature points for some values of the parameters. Okay? Therefore, our solution manifold will change because it's not anymore the solution defined on the time domain, but is the set of the Laplace transform of the solution on the quadrature nodes for every instance of the parameter in our domain. This time the snapshots will be complex vectors. This is we have to define an error estimate that typically are based on the residual. And in this case, since we are in the Laplace transform domain, is the residual on the Laplace transform domain. And this then here is how it is defined. The error estimate is an upper bound of the error, and basically is we have to evaluate the residual on the quadrature points, and we have also here the norm of the resolvent on the quadrature points. Okay, so this has to be cheap to evaluate. Indeed, the residual is cheap to evaluate because this is the expression, and you see that here we have only the reduced solution on the quadrature point, and this is cheap because this is some low dimension. This is not cheap to evaluate because it means that we have to solve eigenvalue problems to compute this. But indeed, there are techniques to approximate and to find an upper bound of this quantity for each instance of the parameter, and we use one of these strategies. So this is then the algorithm to construct the reduced space, and so as before, we find the value which maximizes the error estimate, we compute the solution on the quadrature points, the Laplace transform the solution on the quadrature points, and then we inject on our reduced space. With the strategy I described, we build one reduced space that approximates the solution at the same time on the quadrature points. Another idea can be, we have different quadrature points, we can build different reduced spaces for each quadrature points. And this is indeed what is here in algorithm 3. And we have an outer loop here where for each quadrature point we build a reduced space. Okay. So So now the numerical examples. Okay, so I will use an example that arises from finance, because this is a field where one is interested in knowing the solution on a final time t, not all the evolution of the solution from 0 to the time t, but typically only at a given time, or in some small time windows. So this kind of application are well suited for contour integral methods. So the first one is Black-Scholes model, and we have two parameters, which is one is the risk rate, R, and the other one, sigma, is the variance. Okay, we discretize with 1000 degrees of freedom, and the time window we are looking is 110. This is the range of the parameter. This is how we discretize the parametric set. And this is how we measure the error. So we take the maximum over the discrete set of the parameter and the maximum over the time interval 110. And these are relative error, of course. So this graph shows how behaves the error estimate and the error when we build the reduced space. So the behavior is similar, and the convergence is exponential. And then we have here the error associated to the reduced space built with this strategy. Here is the algorithm where we build one reduced space, so algorithm 2 before. So here we have the exponential decay of the error. Okay, this is a comparison with the local version, so where for each quadrature point we build a specific reduced space. And so we can see that okay, we need more time to build with the second approach, and also we need to save more snapshots. But then, okay, the error is much faster to decay, really much. And typically, in the framework of model reduction, okay, you have to do some effort in building your reduced space, and this is called the offline phase. But then you solve a reduced problem, and which are small size, and this is the online phase. So typically, one wants to put more effort on this offline phase when building to build the spaces. Then, if we have then, let's say, we have gain in the online phase, so if we are faster in the online phase. And here, okay, if we set a target accuracy, it's clear that here we reach it with less, with a subspace of less dimension than with a global approach. So, a strategy, the second strategy should be better for the application. The second problem is the Eston model is an extension of Black-Scholes in 2 dimensions. Black-Scholes was 1 dimension, this is 2 dimensions. And we take 5 parameters here in consideration. So we discretize with 10,000 degrees of freedom. And okay, this is the time interval, the range of the parameters. How we discretize the parametric domain, and how we measure the error as before. So same plot, error versus error estimate. Okay, and then decay of the error. Okay, before with Black-Scholes, we were the error. Of course, we were it was decaying fast, but because it's a problem with 2 parameters. Here we have 5. When we enlarge the parametric space, then we need more snapshots to approximate all the problem, and therefore we need larger reduced spaces. Again, we compare local and global strategies, and again here, okay, at the level of CPU time, now we are faster with the local approach, but still we have to store more snapshots. But then we have always this gain here in the decay of the error. It's much faster. Okay, another numerical result is we compare it with say classical methods. So when we approximate by time stepping method the time problem, and then we apply the reduced basis to that. The time step chosen was 10 to the minus 4. Okay, so here is the method chosen is Crack-Nicholson. So okay, here is the ratio between the time to compute the solution in the online phase with Crack-Nicholson and the time with our method, so the contour integral method. And we can see that we are faster with respect to the number, to the size of the reduced base. So we are faster with the contour integral method. And also, if we look to the decay of the reduced base constructed by a Crack-Nicholson scheme or by the contour integral method, we see that decay is much faster here. This was for Black-Scholes, same for Eston, but now we just consider the 2 parameters here. So the picture are quite similar. Okay, the last application is to hyperbolic problems. So hyperbolic problems are considered challenging for reduced basis, in general for model reduction, because you need a lot of snapshots to well approximate the problem. Okay, this is due to the fact that okay, the Kolmogorov width for some kind of hyperbolic problems has only a polynomial type decays, and this makes it slower and not well suited for reduced basis and model reduction. Okay, why then we should we have to apply contour integral methods? Well, the reason for this slow decay is mainly due to the fact that this problem may have discontinuities, or let's say they preserve discontinuities, like when you don't have diffusion, normally the diffusion has the effect of smoothing your solution. But with hyperbolic problem, this does not happen. For example, if you have a linear hyperbolic problem with a discontinuous initial data, this data is then the discontinuity will travel and will still be present. Or if you have nonlinear problems, then they may develop a discontinuity. So the idea is that okay, our solution manifold is on the Laplace transform domain. For example, if we apply it to the reset function, we see that the Laplace transform is not discontinuous anymore. So we just apply it to a simple 1D linear advection problem, where the parameter here is the velocity. Okay. So and what can be seen is that okay, we used an explicit Euler, very simple, and the contour integral method. So we computed the snapshots, then we put them in a matrix, we perform a singular value decomposition, and we look to the singular values. So if the behavior of the decay of the singular values is they decay with the same order of the decay of the Kolmogorov width of the associated problem. So what we can see is that with the contour integral methods, this decay is exponential. While here, when we apply the time stepping method, so some point it became polynomial here, and it's flat. Then when all the information is injected, it has this jump. But the jump happens when the size is 500, which is too much. And indeed, here, the decay of the error shows that while here the decay is polynomial, here we have the exponential decay with the contour integral method. So to conclude, let's say the work is based on the fact that contour integral method can be very accurate for approximating ordinary differential equation, and also the computational cost is good for the accuracy you can reach. And this feature can be highlighted by using reduced order techniques when you have parametric problems. And also the comparison between the reduction with the contour integral method and with classical techniques based on the time stepping scheme show that we have a gain applying the reduction with the contour integral methods. Also, I didn't mention, but okay, the main effort is to compute the solution on the quadrature points, the Laplace transform of the solution. But these computations are all independent by each other, so this process can be parallelized. While if you apply time stepping schemes, you cannot parallelize because you need the information on the previous time step for computing the next one. And also a nice feature is that actually we can know the solution on a continuous time window. And this is true also at the level of the reduced problem. So for future works, what we want to do is to extend as much as possible the field of application, contour integral methods. So in particular, we want to deal with more complex hyperbolic problems, to treat nonlinear terms, also to apply to matrix equations, and exploiting lower rankness of the solution. Also, well, another problem is that we need an explicit, an analytic form of the Laplace transform of the source term. So this sometimes is not possible, therefore we have to think how to approximate the source term in such a way that then we know the Laplace transform. These are the references, the talks, and thanks for the attention.
Black-Scholes problem again.
Yeah.
No, do the. Oh, yeah, keep going.
Yeah.
Okay, next one.
Okay.
To forward.
Okay.
One more.
One more.
I don't understand. Why are you storing so many snapshots for the local method?
Because, okay, when you do the global method, then I also, I compute the solution on each quadratic point. Then I compress it by an SVD. So let's say if on a quadratic point there are some snapshots, maybe these snapshots are also good to approximate the solution on other quadratic points. Therefore, when you compress, then you gain something. Okay?
Yeah.
With the local approach, since I build a reducer space on each quadratic point, I don't use the snapshots I take from one quadratic point to approximate then the snapshots on the other quadratic points. That's why then we have more snapshots to store with the local approach.
But then what is the value of NR you're plotting for the local? Is it for which quadrature point is it?
So, no, for this NR, this is the blue is for the global approach.
Yeah, that's clear.
And then the red one is for the local.
Yeah, but don't you have different space dimensions at each quadrature point?
Yeah, okay, so for the local one, what I do is I take like one in every quadratic point, for example, one snapshot in every quadratic point, and then I compute the solution of the reducer problem in this way. And then 2, 3, 4. So when you see here like 20, it means that I've been taking 20 snapshots on each quadratic point. Then of course there are some, the reduced spaces have different dimensions on each quadratic points, right? When in the local approach. So at some point, maybe on one node I have a space of dimension less than 20, so I stop when I finish the dimension, and then on the other point I take
so it's the maximum.
Yeah, it's the maximum, exactly. Yeah, exactly.
Okay. And then the second one, if you go to the problem where you can play with explicit Euler.
Yeah.
It's not, so you said you calculate the snapshots with Laplace and you calculate the snapshots with explicit Euler and do the SVD.
Yeah.
So Laplace is calculating the snapshots more accurately, right? But why
in which sense more accurate?
But you say, I mean, it's a bit more of an accurate indicator.
Yeah, well, yeah.
I mean, the snapshots should still be similar even though you're approximating them in different ways. Why is the singular value decay so different?
Because the snapshots with Laplace transform are snapshots on the Laplace transform domain, so they are complex snapshots and they are different. While these are snapshots on the time domain, right? So, for example, if I take this heaviside function will be a snapshot with the explicit Euler, okay? Yeah. But the snapshot on the Laplace transform domain will be this function, so they are different. That's why then you have a different decay.
Okay.
And in particular here, the fact is that if you take a specific time step, a specific size of the discretization space, then what you have is that your discretization computes exactly the solution, okay? And indeed here it is the case because here, okay, which is the solution? Is the initial data that is translated along the lines, and so is the heaviside function which is moving, okay? And so what makes here slow the decay is that you have these discontinuities that moves, and these moves depend from the velocity that is a parameter, and this makes it slow.
Yeah, so I guess the local approach is very advantageous if you have discontinuities because you can treat them.
You can
avoid. They don't affect your global thing, especially.
Yeah, exactly. Okay, of course the problem is that you need to treat nonlinear terms because they are more interesting. Okay, that's still easy now to do. And also, okay, the problem on this hyperbolic equation is that also the condition of the system grows very large with respect to the size.
And what's the challenge here with using the challenge in using the contour integral for nonlinear functions, or what's the problem?
Okay, the problem for what I've tried is when you develop the discontinuities. Because, okay, you can approximate the nonlinear term by some Picard iteration, these things. The problem is that, okay, at some point you develop a discontinuities, and where then you arrive to that point doesn't work. So, to figure out how to do that. Okay, that's it.
More questions? I wanted to ask you, so I would be interested in using these kind of methods for hard, let's say, time-dependent problems. But I would guess there's no free lunch, right? Because the inverse of your Laplace transform has a really fast increasing rate, of course, because you have the positive exponential, so maybe you have trouble inverting it for long-term simulations. So I wanted to know if this is an issue, and if it is, maybe you can use another transform, so maybe trivially Fourier.
When you are saying when you want to go far in time and to compute the solution far in time.
If I want to compute my solution for a long time, so that
long
when
time,
I
okay.
invert
Yeah.
my Laplace transform, I have to invert like an exponential to the a.
Yeah, okay, so I tried until like t equal 100 and these things, it everything works. Because, okay, when you construct the integration contour, you actually take into account that exponential term. So if the problem is that, okay, if you put t equal 100, 1000, then you have the exponential term to this expression, no? But then, okay, if you place you have also, okay, let me go back to some slides where I can point to it. Okay, for example, yeah, for example here, no, because, okay, this is the associated solution to the linear system, and then you have here the exponential term, okay. So you see here you have also the complex point, right, zeta. So when you construct the integration contour, this is placed in such a way that if you have large times, then it will be shorter. Why? Because with large times, the error decays faster when you go to the left, to the negative part of the complex plane, right? Because here you will have the real part which is negative. So these things will make the error going very fast to the accuracy you want. The problem is that okay, you have a part of the integration contour which is on the positive part, okay. But then okay, you say go back to the beginning. Okay, so like here maybe. Okay, you can place it okay very close to the origin, for example. Then okay, then it depends how conditioned is your system. Because if it's a bad condition, then I think there is not so much you can do. If it's well conditioned, I think you can go even very large.